In today's video, we will see the charging and discharging of a capacitor experimentally. First, we will see the charging of the capacitor using a DC power supply, and afterwards we will see using a function generator. Here I have constructed this circuit where we have a single resistor of 1 kilo ohm, as you can see here, and we have a capacitor which is 10 microfarad. And you can see those two components on the breadboard connected in series. The red wire is connected to the positive terminal of the voltage source, and the black wire is connected to the negative terminal. So we have this 10-volt power supply connected to a resistor, R, and then connected to a capacitor, C. The product of the resistance and the capacitance, RC, is called the time constant. As you can see here, it's represented by this symbol tau. It is called the time constant. And resistance and capacitance, when multiplied together, the unit becomes time. So in our case, we have a 1 kilo ohm resistor and a 10 microfarad capacitor. So when I multiply these two, the result is 10 millisecond. So this means for this circuit, my time constant is 10 millisecond, which we will discuss in future videos what it means. But for now, we should know that the charging time of this capacitor would be approximately 5 time constants. So 5 time constants will become 50 milliseconds. So based on these components, the capacitor should charge within 50 milliseconds, which is a very short period of time. Initially, the capacitor will be not charged, so the voltage across the capacitor will be 0. The power supply will produce a current through the resistor R, which will start charging this capacitor. And as the capacitor starts charging, the voltage drop across the resistor will slowly decrease. And as such, the current through the circuit will decrease as well. So eventually, after 50 milliseconds, the capacitor will be completely charged to 10 volts, and the current in the circuit will go to 0. So we will see that the voltage across the capacitor should reach 10 volts very quickly, that is within 50 milliseconds. We will use multimeter to measure the voltage across the capacitor, and of course the multimeter will not be able to tell us the transient, which is only 50 milliseconds. The multimeter will just show us that the capacitor has been charged. So this is our circuit. We have this 1 kilo ohm resistor connected in series with this 10 microfarad capacitor. And the resistor is connected to the positive terminal, which is 10 volts. And then the capacitor is connected to the negative terminal, which means 0 volts. This is the voltage produced by the power supply, which is 10.01 volts. And if I want to measure the voltage across the capacitor, I can see it over here. This is the voltage across the capacitor, which is also 10.01 volts. So we can see that the capacitor has already been charged by the power supply. We can also measure the voltage across the resistor. So if I touch the two sides of the resistor, we see that the voltage across the resistor is 0 volts. So if I have a 0 volt drop across the resistor, this means the current through the resistor must be 0 amperes. Therefore, the circuit is open because of the capacitor, because the capacitor is completely charged and it is not allowing any more current to flow through the circuit. So therefore, the current in the circuit is 0, which is causing a 0 volt drop across the resistor, and the capacitor is completely charged to 10 volts. I can change the voltage of the power supply, and if I increase it, then the capacitor will be charged to the higher voltage. So the capacitor will very quickly, within 50 milliseconds, as we calculated, the capacitor will charge to its new value in that time. So let's see, if I increase the voltage of my supply to, let's say, about 15 volts. So my supply voltage is now about 14.9. So let me check this. So you can see on the multimeter that the supply voltage is 15.1 volt. That is the voltage produced by the supply. And now let's see how much voltage do we have across the capacitor. And we see across the capacitor is exactly the same voltage as the power supply. So when I increase the voltage of the power supply, the current flow in the circuit for a short period of time, which charges the capacitor to the new voltage. And now, once the capacitor is charged, then the current in the circuit goes back to 0, and you can see the voltage across the resistor is 0. Similarly, I can decrease the voltage of the power supply. So we see the voltage across the capacitor right now is 15 volts. If I decrease the voltage of my power supply to, let's say, back to 10 volts, this would mean that the voltage across the capacitor is actually larger than the voltage produced by the battery. So therefore, the capacitor will actually produce a current in this resistor in the opposite direction. So the extra energy that was stored in the capacitor will actually go back to the power supply. And when the current is produced by this capacitor, the voltage of this capacitor will start decreasing until it reaches the 10 volts produced by the battery. And then the final voltage will be 10 volts across the capacitor and 10 volts produced by the battery. So let's see if we can show that. So as we can see, the voltage is 15 volts across the capacitor at the moment, and the voltage produced by the power supply is also 15 volts. Now, if I decrease the power supply, we should expect that the voltage across the capacitor should also decrease and become equal to the voltage of the power supply. So let me try to show you while I'm touching these probes over here. So I have 15 volts across the capacitor, and now we will decrease the voltage of the power supply. And you can see the capacitor discharges immediately. And now the power supply voltage is 12, 11, 10, about 10. So 10.05. And you can see that the capacitor will also discharge to the new value. Now, another thing that I want to show is that what will happen if I turn off the power supply? If I turn off the power supply, then this means that the voltage produced by the supply between these two wires, the red and black, that voltage will go to zero. And then the energy stored in the capacitor will actually cause a current I to flow in the resistor, and the circuit would be complete, and the capacitor will discharge through this resistor, through the power supply as well. So the capacitor's stored energy will be used to produce a current in the resistor, and the capacitor will discharge through the resistor and the power supply. So let's see, right now the capacitor is charged to 10 volts, and if I turn off the power supply, we should expect that the capacitor will discharge. And you can see now the voltage across the capacitor is 0.1 volts, 0.0, and it is almost zero now. If I turn the power supply again, the capacitor should charge back to 10 volts. All right. So the reason why the capacitor is discharging is that there is a path. When I turn off the power supply, the voltage produced between the positive and the negative terminal becomes 0 volt, which is kind of a short circuit. So therefore, the capacitor has a path to discharge. Now, what will happen if I do not provide that path? And I can do that by disconnecting the power supply from the circuit without turning it off. So I want to keep the capacitor charged, but I just want to remove the power supply. So to do that, right now we can see that the capacitor is charged to 10 volts. So what I will do is that I will remove this negative terminal. All right. And now I can remove the positive terminal as well. So now the capacitor has no path to discharge. So if the capacitor was charged to 10 volts, it should still be charged to 10 volts. And now I can turn off the power supply and the capacitor should not get discharged. So let's see how much voltage do we have right now across the capacitor. So the positive probe of the multimeter is connected to the positive wire of the capacitor. So now let me connect the negative side, and you can see it's 9.9 volts. So the energy stored in the capacitor is still there, but we can see that the voltage of the capacitor is slowly decreasing. It's 8.8, 8.7. And the reason why it is decreasing is that we have the multimeter, the voltmeter, now connected in parallel with the capacitor. And the multimeter, although it has, so the multimeter, when we are using it as a voltmeter, it has a very high resistance, but still it has a resistance. So now you can imagine that there is a resistor, a very large value of resistor connected in parallel with the capacitor, which is providing a path for the capacitor to discharge. And the capacitor is discharging through the multimeter. Now, you see this discharge is happening at a constant rate, for example, 5.8, 5.7, 5.6, and so on. If I remove the multimeter, now there is no path for the current to flow. So the capacitor should retain its charge. And if you remember, we were about 5.9 or 5.8 volts. And since I removed the multimeter, the capacitor voltage should have stopped decreasing. So now if I touch it again, I should expect that the voltage will start from the same point where we left. So let's check that out. I touch it again and you see 5.4, 5.3, 5.2, 5.1, 5 volts, and now I stop it again. So I want to remember that we stopped discharging at 5 volts. And if I wait a few seconds to see if the capacitor voltage will remain the same, and I hope it remains the same because there is no path for the capacitor to discharge. And now let's touch it again, and you see 4.9, 4.8. So this demonstrates that the capacitor has energy stored in it, and it will discharge only if a path for the current is provided. Using this power supply and multimeter, we were able to see the charging of the capacitor and discharging of the capacitor, but we were not able to measure the time it took for the capacitor to charge and discharge. So to be able to demonstrate how much time does it take for the capacitor to charge and discharge, we will use a function generator, which is shown over here. This is a function generator. It can produce different waveforms, different frequencies, and the output of the function generator is this BNC cable, which we will connect to the circuit. To be able to see the voltage across the capacitor and across the resistor, we will use the oscilloscope. I will be posting videos in which we will show how to use the function generator and how to use the oscilloscope. If you are not familiar with these equipment, please watch those videos. To see the charging and discharging of the capacitor, we will use the function generator and apply a square wave as shown over here. So this is the symbol of the function generator. And this waveform is just to show that we will be producing a square wave or a rectangular wave, which is just to say that we will have a voltage that will be high for a certain period of time, and then it will be low for a certain period of time. What I will do is that I will make this voltage about 5 volts and then 0 volts, and then 5 volts and then 0 volts. So what it will do is that this function generator will produce a waveform which will charge the capacitor and then go back to 0. Then charge the capacitor, then go back to 0. So the voltage will be pulsing at a frequency that we can adjust. When the function generator produces 5 volt, it will produce a current through the resistor, which will charge the capacitor to 5 volt. However, the capacitor will not charge to 5 volt immediately. It will take some time. And as we previously calculated, that the amount of time it will take will be 50 milliseconds. So the capacitor voltage will go from 0 to 5 volt in 50 milliseconds. Then the function generator voltage will go back to 0 volts. So when the function generator becomes 0 volts, then these 2 points become shorted. So that this path is now 0 volts over here, so the capacitor can discharge. So the capacitor has been charged to 5 volts, but now the function generator goes to 0 volts, so therefore the capacitor will discharge through this resistor, and it will also take 50 milliseconds for the capacitor to discharge. So the green curve over here is the charging of the capacitor, and here the green is actually the discharging of the capacitor. The white square wave is the output of the function generator. So the function generator produces 0 volts, and then 5 volts, then 0 volts, and then 5 volts. Now, I need to adjust this frequency of the function generator so that we have enough time, or we give enough time for the capacitor to charge and discharge. So if I say that the capacitor will charge in 50 milliseconds and it will discharge in 50 milliseconds, so therefore the time period of this one pulse from the function generator should be 100 milliseconds. So if the time period is 100 milliseconds, this means the frequency will be 1 over the time period, which is 1 over 100 millisecond, and this is equal to 10 hertz. So I will apply a square wave from the function generator at a frequency of 10 hertz, and then we can see those two waveforms, which will tell us how the capacitor is charging and how it is discharging. We were not able to see these dynamics using the multimeter, but the oscilloscope should be able to show us this very clearly. So here we can see that we have about 5 volts and then 0, and then 5 volts and then 0. So the x-axis is the time scale, and the vertical axis is the voltage scale. Right now, the blue channel, which is channel number 2, I have 2 volts per division. So therefore, I have 1 division, 2 division, and 2.5. So which is 5, which represents 5 volts. This is the waveform produced by the function generator. And you can see from here that I have set the frequency to 10 hertz. So you see I have clicked 10 and 1 over here. So that's a 10 hertz frequency. And we can see that the frequency is 10 hertz because the time per division is 25 milliseconds. And we have 1, 2, 3, 4. We have 4 divisions. So 25 milliseconds times 4 is 100 milliseconds. So that's our time period, which corresponds to a frequency of 10 hertz. Now I want to see the voltage across the capacitor. For that, I will have to use a second probe of the oscilloscope. So now I have connected the second probe of the scope, which is the yellow curve on the oscilloscope. And you can see that the voltage across the capacitor changes slowly. It cannot change abruptly, as we discussed in the previous lecture. So the voltage across the capacitor changes slowly as a function of time. And you can see that it takes about 50 milliseconds or maybe slightly less than that to completely charge the capacitor. And then it takes the same time to completely discharge the capacitor. So you see during this time period, the capacitor voltage is increasing exponentially and the capacitor is getting charged. Over here, the capacitor is getting discharged. So using a function generator and an oscilloscope, we are able to see the voltage across the capacitor in real time. Now, I want to see what will happen if I decrease the frequency of my input signal, the function generator. So let's say I decrease the frequency to 5, about 5 hertz. So you see, the charging time and discharging time of the capacitor did not change. It is still the same. And now the capacitor gets charged in the same amount of time as before, but then for the rest of the time, so you see the capacitor gets charged over here, and then for the rest of the time, there is no current in the circuit, and the capacitor just stays the same voltage, which is the supply voltage. In this case is 5 volts. So the capacitor is just charged, and then it is waiting for the next cycle to get discharged. So the charging and discharging time has nothing to do with my frequency. As you can see, the charging time is the same, and discharging time is the same as well. Now let's see what will happen if I increase the frequency. So let me go back to 10 hertz. So this is about 10 hertz that we have. And now I will increase the frequency by a factor of 10. So this is 100 hertz. So at a frequency of 100 hertz, let me zoom in on the time scale. So you see now, at this time, the function generator goes to 5 volts. And the capacitor starts to get charged. So the capacitor is charging. So the voltage across the capacitor is increasing. But this time period is very small. So the capacitor does not have enough time to charge sufficiently. So the capacitor voltage goes from here to here. So let's say it increased by 1 volt approximately. And then the function generator output goes to 0. And when that happens, the capacitor then starts discharging. So the capacitor starts from here, which is about 3 volts, and then it discharges back to 2 volts. And then the function generator goes back to 5 volts again. So the output of the function generator is changing so rapidly that the capacitor does not have enough time to either charge completely or discharge completely. So it is kind of staying in between the two extremes, the maximum and the minimum. Let me increase the frequency by a factor of 10 again. So now I will make the frequency 1 kilohertz, which is 1000 hertz. And when I do that, now you can see that there is barely any time for the capacitor to either charge or discharge. So therefore, the voltage across the capacitor looks like it is just constant at the middle. This property of the capacitor is used a lot in the design of filters. All right, so we are back to the 10 hertz frequency. And now I want to show if I increase the frequency slowly instead of a factor of 10, we can see that at this time the capacitor is still getting charged and discharged completely. But if I keep on increasing the frequency, then the capacitor will be not able to charge fully. And you can see here now the capacitor is slightly less than fully charged. That's it for today's video. I hope you enjoyed this lecture. If so, please do subscribe my channel. I'll see you next time, and bye for now.